Okay, welcome back, friends. Yesterday, we have derived what is called a Maxwell's equations. Very popular, very interesting. Maxwell's equations. Okay. So the contribution of the Maxwell was this one, the displacement current. And he has named all the four equations as a Maxwell's equations. Clear? And then so the electrostatics and magnetostatics are just a special case of EM phenomena. You can obtain the static fields from these things. Okay. And then we have seen what is called a EM phenomena. What is that EM phenomena? Time varying electric field giving magnetic field, space varying magnetic field, and time varying magnetic field is giving space varying electric field. Again, electric field is giving magnetic field is giving electric field, and so on. This is called EM phenomena. So, without this term displacement current, you cannot imagine what is called a EM phenomena. So, the time varying electric field is also giving the magnetic field. That is what said by Maxwell himself. Clear? Yes. So what else we have discussed yesterday session? There is a thing. So derivation, and I have given the interpretation of the each and every equation. These two are called effect equation. These two are called source equations. And the special name given for this equation is intrinsic relation. Clear? Yes. Now, let us proceed further. Now we were discussing what is called a significance of displacement current or displacement current density. I have explained what is called a, because of this displacement current, there is a EM phenomena. Fine. Let us take one more significance here. We want to understand how the EM phenomena exists inside the perfect conductor. What happens to the EM phenomena inside the perfect conductor? Number 2. EM phenomena phenomenon inside perfect conductor. What is the conductor? Perfect conductor where the conductivity tends to infinity. Is called perfect conductor. Can EM phenomena survive inside the perfect conductor? Yes. Let us try to understand that concept. Very interesting. See here, and it is also helpful in our boundary conditions as well as in your electrical engineering also. Suppose we know that inside the perfect conductor, electric field cannot survive, cannot exist. That we are having the idea about that one. But let me show you with the help of examples here. See here, we know that J is equal to sigma into E and D is equal to epsilon into E. That all we know. Here, how this E can be written, beta? Consider J is equal to sigma into E. So from here, E is equal to J by sigma, where sigma tends to infinity, beta. J by infinite, beta. So anything for infinity is 0. So the electric field is equal to 0 inside the perfect conductor. This is with the help of equations. So inside the perfect conductor, the electric field is 0. Now let us consider the Maxwell's equations. What are the Maxwell's equation? What is the first Maxwell equation? I'll write down these Maxwell's equations one more time. So what is the first Maxwell equation, beta? Del cross H is equal to sigma into E plus dou by dou T of epsilon into E. What is the second Maxwell equation? Del cross E is equal to minus dou by dou T of mu into H. We know that here electric and magnetic field both are related. Electric field will give magnetic field and magnetic field will give electric field. Yes. So here inside the perfect conductor, the electric field is 0 unconditionally. 1, 2, 3 lines, always 0. 1, 2, 3 lines. Here it is always 0. So what happens to satisfy these two equations simultaneously? That will force the magnetic field also to become 0. Because magnetic field is dependent on electric field and vice versa. That will make the magnetic field also to become 0. So as the electric field is 0, as for EM phenomena, as electric and magnetic field both are dependent on each other, so that will make the magnetic field also to become 0. So what is the final conclusion here? Inside the perfect conductor, EM phenomena cannot survive, isn't it? Let me show you symbolically like this. We know that electric field is dependent on magnetic field and vice versa. Here the electric field is unconditionally 0. 3 lines. It is always 0 inside the perfect conductor. 1, 2, 3. So this will make the magnetic field also to become 0. So what is the final conclusion here? Electric field inside the perfect conductor. EM phenomena cannot survive inside the perfect conductor. All fields are 0. Or in other words, good conductor is a high loss medium for EM phenomena. Okay. So what is the statement beta here? EM phenomenon can't survive inside the EM phenomena can't survive inside the perfect conductor. Or all fields are 0 inside the perfect conductor, you can say. So the EM phenomena cannot survive inside the perfect conductor. So where it can survive, there is no other way. It will come and sit on the surface of the conductor. Suppose if you use the solid conductor for the transmission of electromagnetic energy from one point to other point, the concentration of energy happens on the surface, isn't it? That is what popularly known as a skin effect in your electrical engineering. Isn't it? Yes. So EM phenomena can't survive inside the perfect conductor beta. Clear? So this is the other thing which I wanted to highlight. This is the first one. Here I have explained EM phenomena. So we have considered the same EM phenomena inside the conductor. So electric field is 0. That will make the magnetic field also to become 0. So the EM phenomena cannot survive inside the perfect conductor. Let us take two more significances here. I'll consider what is called capacitor example beta. Number 3. Capacitor. What is the capacitor? What is the capacitor beta? There are two plates separated with some dielectric. Okay. These are two plates separated with some dielectric. The dielectric can be air also. Now here my basic question is, what I know is a capacitor is a can you treat this as an open circuit? One plate, one more plate separated with some dielectric. Why can't you treat them as a open circuit? If that is an open circuit, then how the current flow can happen? I is equal to C dV by dt. Here my fundamental question is, how current flow can happen inside the capacitor? Any answers from your side? Any answers from your side? Capacitor is an open circuit beta. Displacement current, because of the displacement current, charge distribution. Okay, charge induced displacement. Okay, okay, very good, very good. Due to the charge, yes. See here, we know from the Ampere's law, curl of H is equal to J plus dou D by dou T. That means the magnetic field is due to flow of charges and also due to the time varying electric field. Let us consider for the capacitor for the positive of cycle. If you consider for the positive of cycle, the current flow will be like this. Okay. Suppose if you consider, I'll just magnify that capacitor beta. I'll draw here. Here is the capacitor. For the positive cycle, what happens? All the positive charges will come and sit here. And all the negative charges will come and sit here. What happens? There exists an electric field from positive to negative charge. What kind of electric field is this? Is a time varying electric field. So when you have a time varying electric field, what is called, there will be a displacement current, JD. JD is equal to dou by dou T of epsilon into E of T. That means time varying electric field will also give the magnetic field. There will be a magnetic field around it, which is given like this. There is a magnetic field here. So what is this one? Is a electric field. So there is a current flow is happening here. Here also magnetic field exists around this one. Magnetic field exists around this one due to the flow of electrons. So that means the continuity of the magnetic field is maintained throughout the circuit. How it is maintained, beta? Here it is maintained with the flow of charges. In between, it is maintained with the time varying electric field and flow of charges. So as the continuity of the magnetic field is maintained throughout the continuity of the magnetic field is maintained as the continuity of the magnetic field is maintained throughout the circuit. So this will going to act like what? Closed circuit. Okay, beta. So to put it in a simple words, what you can say? To put it in a simple words, what you can say? You can just say that between the two plates, the current is supported by the displacement current. But if you want me to elaborate that one, what you can say? You can say that the electric time varying electric field is established. That will in turn will give the magnetic field. So in the terminals of the capacitor, it is supported by the flow of charges. The magnetic field is supported by the flow of charges. Between the plates of a capacitor, it is supported by the time varying electric field. So the continuity of the magnetic field is maintained throughout the circuit. So as there is no discontinuity, this circuit will be treated as going to behave it as a closed one. Or the single line statement here is for the parallel plate capacitor, conduction current, magnitude of the conduction current is equal to displacement current. Okay. So what happens for the instead of AC supply, if you give the DC supply, instead of AC supply, if you give the DC supply, what happens if you give the DC supply? This electric field will be constant. And what is the differentiation of the electric constant is zero. That means the displacement current is zero. So it cannot excite any magnetic field. So there will be a discontinuity of magnetic field between the plates. Yes. So that is the reason why capacitor acts like an open circuit for the DC supply at the steady state. Okay. So what you need to remember for your exam is only this one. Conduction current is equal to displacement current. But if at all, if you get a question, if any interview, if any interviewer asks regarding this one, this is the explanation you need to give. Fine. So we have done it for we have understood EM phenomena. We have understood what is called EM phenomena inside the perfect conductor. We have understood how the current flow is separated between the plates of a capacitor. Let us have one more thing, beta. I'm going to turn the page here. Low frequency circuit analysis. Number 4. Low frequency circuit analysis, or low frequency circuit analysis will be taken for the frequencies less than 1 megahertz. You can check out all your circuit theory problems will not go beyond 1 megahertz of operation. Anyhow, for the electrical engineering, we'll be dealing only with the 50 hertz and 110 hertz, very low frequency. The present day technology can support the frequency generation up to 3000 terahertz. Compared to the tera, 10 to the power of 15, the mega is negligible, is a low frequency. Or DC circuit analysis. Anyhow, what is the meaning of DC circuit? It is 0 hertz. You are dealing with a very low frequency beta. What does that mean? As you are dealing with a very low frequency, here dou by dou t is proportional to the frequency. Rate of change of time is proportional to the frequency. As you are dealing with a low frequency implies the low value of dou by dou t. Low frequency implies low value of dou by dou t. So we can do this approximation here. Dou d by dou t beta. What did they are? For what the engineers have done, as I said earlier, when they observed these Maxwell's equations, actually this is what the electrical engineering is. You need to apply these equations to understand the electrical engineering. Machines, motors, transformers, circuits, RC tube circuits, resonant circuits, are two-port networks, isn't it? To understand the different things, these are the equations you have to use. Amma. These are the equations you need to use to understand the different aspects of electrical engineering. Long length transmission line, capacitor, inductor, whatnot. See here how complicated equations they are. That is the reason why what the engineers have done, they have developed some approximated theory. They have developed some simplified theory, which is best suited for our electrical engineering. Why? Because electrical engineering happens at the lower frequencies, isn't it? 50 hertz, at the most 110 hertz. Lower frequencies. As we are dealing with the lower frequencies, you can do certain approximations. So they have observed that thing and they have done some approximation and which had led to the very simplified theory. Fine. Yes. But whenever it is required, here and there in the electrical engineering, you will talk about these things. Faraday's law, you talk about this source for the magnetic field, you talk about the Ampere's law, isn't it? All these things are used in the electrical engineering. Fine. So what the engineers have done is this one. So as you are dealing with the lower frequency, 50 hertz, 110 hertz, less than megahertz. So they have made one approximation here. They have made this approximation. Dou d by dou t, comma, dou b by dou t are negligible. Are negligible. That means there is a EM phenomena, no doubt in that. But the EM phenomena is very weak. Let me show symbolically. It is not strong like this. No, it is weak. Because it is a very low frequency. The interaction between the electric and magnetic field is not that much strong. It is very weak. So what are the Maxwell's equation? Let us consider the Maxwell's equations. First Maxwell equation. Del cross H is equal to J plus dou d by dou t. This is approximated to J beta. Second one, del cross E is equal to minus dou B by dou T is approximated to 0. So these are the approximations are done for the low frequency analysis. So consider this one beta. Consider this equation. Del cross H is approximately equal to J. Now I'll apply the divergence on both sides. What happens? Divergence of curl of H is equal to divergence of J. So divergence of a curl of a vector is equal to 0 beta. So 0 is equal to divergence of J. Or you can apply what is called a divergence theorem. What is the divergence theorem? Closed surface integral of JdA is equal to volume integral of divergence of J into dV. What is the divergence of J? Divergence of J is equal to 0 beta. So it will become closed surface integral of JdA is equal to 0. Keep this one aside. Similarly, what you can do is this one. Consider del cross C is approximately equal to 0. You can use what is called a Stokes theorem. What is the Stokes theorem, beta? Closed line integral of EDL is equal to surface integral of del cross E dot dA. What is this del cross E is equal to? Is 0. That means closed line integral of EDL is equal to 0. Array. Observe here, beta, this one. You can do some approximations at the lower frequencies. What is saying? The algebraic sum of voltage drop in the loop is equal to 0. Array. What this is saying, beta? The net current is equal to 0. Array. Current entering the closed surface is equal to current leaving the closed surface. Array. It is here somewhere we have heard somewhere, isn't it? It looks like as if we have heard something about this one in the earliest memory in our past life. Punarjanma. Not Punarjanma, not in the past life, in this life itself. In the circuit theory, what is called KVL and KCL. Yes or not? KVL, KCL, beta. Yes or not? So that is how they are developed. The approximation of this one was led to the what is called a circuit theory. Let me turn the page here. So we'll do one more thing there in the circuit theory. Suppose, for example, here is a resistor, beta. Here it is an inductor. Here it is a capacitor. So there is a magnetic field here. There is an electric field here. Whatever the magnetic field is there, is only there inside the. It's only there inside the inductor. The magnetic field from here is not interacting with this one. The electric field from here is not interacting with this one. That means fields are localized. And what kind of circuit model we are taking? Lumped electrical circuits. What is lumped electrical circuits? Lumped components means which we can remove physically and you can place them. Lumped and distributed model. So the fields are localized, beta. What kind of nature here? The fields are localized. Why? Because whatever the field is there in the inductor, it is only there. It's not interacting with the other things. That is what you do in your circuit theory, isn't it? The fields are localized. Why? Because you are dealing with the low frequency. So what it is? Fields are localized, beta. So approximation of these equations to the lumped electrical circuits and for the localized fields will lead to the what is called KCL. This will lead to what is called a KVL. Okay. So final conclusion. The approximation of equations closed line integral of JDA is equal to 0, comma, closed line integral of EDL is equal to 0 to lumped electrical circuits and for localized fields leads to KCL, KVL respectively. Okay, just to create, just these are the some of the things which I wanted to highlight regarding this Maxwell's equations beta. Like this, you will find number of applications of Maxwell's equations, but major things are this one. Okay, let us have some questions here so that you will appreciate. Already we have done these questions. We have done the questions on Maxwell's equations individually. We have done the questions on this one, this one, this one. Okay. But let us do some more questions here. Some new models of questions, which was never asked in the GATE exam so far. Question. In free space, E is equal to 20 cos omega t minus 50x y cap volt per meter. Calculate. Question A. Displacement current. Question B. H. Question C. Angular frequency omega. Its units are ampere per meter square, ampere per meter, radian per second. Okay, so it is for the free space beta. Modify the Maxwell's equations for the free space, and from there you will get the things. Now let me write down the solution here. Let us consider the free space beta. What is the meaning of free space? Conductivity is equal to 0, mu is equal to mu naught, epsilon is equal to epsilon naught. So what happens to the conduction current density? J is equal to, we know that sigma into E beta, which is equal to 0. D is equal to epsilon naught into E, and then B is equal to mu naught into H. Okay, just substitute in the Maxwell's equations. What is the first Maxwell equation? Del cross H is equal to J plus dou D by dou T. Second Maxwell equation is del cross E is equal to minus dou B by dou T. How this can be modified, beta? This can be modified as del cross H is equal to epsilon naught into dou E by dou T. And then del cross E is equal to minus mu into dou H by dou T. This is nothing but a displacement current, JD. Conduction current is 0, isn't it? Fine. Let us answer the first part of the question. What it is, beta? JD. What is JD? Epsilon naught into dou E by dou T. Okay. Just substitute there. What is displacement current density, JD? JD is equal to epsilon naught into dou by dou T of 20 cos omega T minus 50x into y cap beta. Okay. So what it is? JD is equal to differentiation with respect to time. So it will become minus successive differentiation 20 omega epsilon naught into sine omega T minus 50x into y cap. Units are ampere per meter square. Is that clear? Yes. So it is minus 20 omega epsilon naught sine omega T minus 50x y cap. Units are ampere per meter square. That is the first part of the question, very straightforward. Now let us focus on the second part of the question, beta. He has given the E and is asking for the H. How can you find out? E and H are related by these equations. You can use any one of the equation. As we have already evaluated this one, let us use this equation. Clear? Let me turn the page here. The second part of the question, you have to find out H. So the E and H are related by the first two Maxwell's equations. Let us consider the first Maxwell equation, which is del cross H is equal to JD. Del cross H is equal to epsilon naught into dou E by dou T. Expand this one better. X cap dou by dou X HX. Here it is Y cap dou by dou Y HY. Here it is Z cap dou by dou Z HZ. Which is equal to, what is this one? This is JD, displacement current density. Displacement current density, this entire thing. Minus 20 omega epsilon naught sine omega T minus 50x y cap. Okay, fine beta. See here carefully. What you have noticed here, there is a y component here. So on the left side also, I'll going to equate it with the y component without wasting my time. So what is the y component on the left side? So minus y cap into this minus this into this. Already one more minus is there. It will become plus. Clear? Yes. So it will become dou by dou x of hz minus dou by dou z of hx is equal to 20 omega epsilon naught sine omega t minus 50x. Beta, see here. Right side, which variation you are having? Right side you are having, just a minute, beta. Sorry for the disturbance. Yes. So what you have noticed here, right side, here is a X variation beta. Here is a X variation. So the left side also there will be X variation. There won't be Z variation. Means what? You can equate the X variation on the right side and left side. It implies that dou by dou Z of Hx beta. So it must be equal to 0, isn't it? Because if you see the right side, there is no Z variation. This happens for the two cases. One is Hx should become 0. The other one is Hx must be constant. Hx cannot be constant beta. Why? Because we are dealing with the time varying fields. I'll repeat again. Hx cannot be constant because we are dealing with the time varying fields. Let me go back. Time varying electric field will give space varying magnetic field, and time varying magnetic field will give the space varying electric field. So Hx, no field cannot be constant here because we are studying this one under the context of time varying fields. So this is not possible. So the only possibility is this one. So the Hx must be equal to 0. I'll repeat one more time. So here right side, which variation? X variation. Left side also you must consider X variation. Clear? So there is no Z variation here. So this part must go 0. That part must go 0. That happens only when Hx is equal to 0 or Hx is equal to constant beta. It cannot be constant. Why? Because we are dealing with the time varying fields. So it must go 0. So here it is. This implies dou by dou x of Hz is equal to 20 omega epsilon naught sine omega t minus 50x beta. Okay. So from here you can write dHz is equal to 20 omega epsilon naught sine omega t minus 50x into dx beta. You want the expression for Hz beta. Yes. So I need to integrate this one. Hz is equal to integral of 20 omega epsilon naught sine omega t minus 50x into dx. Yes. Okay. So here, how do you integrate this one? Here it is 20 omega epsilon naught sine omega t minus 50x into dx beta. So what is the integration of this one? Sine integration is minus cos. Here it is. And 20 omega epsilon naught minus cos omega t minus 50x divided by 50 minus 50. Clear beta? Yes. So what is the Hz expression? I'm going to turn the page here. Oh, what did I say? So Hz is equal to 2 by 2 omega epsilon naught by 5 cos omega t minus 50x. So the H is equal to 2 omega epsilon naught by 5 cos omega t minus 50x. Z cap units are ampere per meter beta. So this is the expression for H. And what is the third part of the question, beta? Let us discuss the third part of. Let me go back. The third part of the question is you have to find out this angular frequency omega. ABC. Yes, what is the third part? You have got a magnetic field expression. And the electric field expression is given in the question. Let me go back. The electric field expression is given in the question. You can take this electric field and magnetic field expressions and you can just substitute here in any one of the equation, this one or this one. So that you will get some unknown value, angular frequency omega. As we have already used this one, let us use this one. Second one. Second Maxwell equation. Okay. Let me turn the page here. So consider second Maxwell equation. What it is? Del cross E is equal to minus mu naught into dou H by dou T. Expand this one beta. X cap dou by dou X. Which component of electric field is given? Y component beta. So here it is 0. Here it is Y cap. Dou by dou Y. Here it is EY. Here it is Z cap. Dou by dou Z 0. Which is equal to minus mu naught into dou by dou T. Which component of magnetic field is given? HZ component. So without wasting my time, I'll just equate the Z components on both sides. Yes. I'll just equate the Z components on both sides. So what is the Z component on the left side beta? Z cap into this minus this into this. That is dou by dou X into EY, which is equal to minus mu naught into dou by dou T into HZ. Just substitute here dou by dou X of EY beta. What is EY? Let me go back. This is EY. 20 cos. What it is? 20 cos omega T minus 50 X minus mu naught into space will not be sufficient. I'll write here minus mu naught into dou by dou T of HZ. What is HZ? This entire thing. 2 omega epsilon naught divided by 5 cos omega T minus 50x. Differentiate this one beta. Here it is minus 20 sin omega T minus 50x into minus 50, which is equal to minus mu naught into 2 omega epsilon naught divided by 5. Here it is sin beta. Minus sign. One more minus sign omega T minus 50x into omega. Yes. So how this will be modified? Sign on left side and sign on right side will cancel out. Here it will become 2050, which is equal to mu naught epsilon naught into omega square 2 by 5 beta. Yes. Let me turn the page here. So what you have got finally is mu naught epsilon naught omega square, which is equal to 2500. So the omega is equal to 50 divided by square root of mu naught into epsilon naught. What is this mu naught value? Is 4 pi into 10 to the power of minus 7 Henry per meter. What is epsilon naught value? 1 by 36 pi into 10 to the power of 9 Farad per meter. So just substitute here. You can check out these values. 1 by square root of mu naught epsilon naught will be equal to 3 into 10 to the power of 8 beta. So just substitute there. So angular frequency omega is equal to 50 into 3 into 10 to the power of 8. So here it is 150 into 10 to the power of 8 radian per second. So single statement, 3 questions we have done. Let us have one more question. Is it clear, beta? Yes, we can find the h from the second equation also. Yes, you are correct, beta. Very good, Mr. Swain. Let us have one more question from the EC paper. I'll going to turn the page here. Here is a question, beta. A parallel plate air filled capacitor has plate area of 10 to the power of minus 4 meter square and plate separation of 10 to the power of minus 3 meters. It is connected to a 0.5 volts, 3.6 gigahertz source. The magnitude of displacement current is, options are given, 10 milliampere, option B 100 milliampere, option C 10 ampere, option D 1.59 milliampere. Okay, beta? Yes. So for a parallel plate air-filled capacitor, it is air-filled capacitor has a plate area of 10 to the power of minus 4 meter square and the plate separation of 10 to the power of minus 3 meter. It is connected to 0.5 volt, 3.6 gigahertz. See, such a high frequency. It is an easy question. Whatever it may be, the magnitude of the displacement current is. What we know for a parallel plate capacitor, magnitude of the conduction current is equal to magnitude of the displacement current. So find out the conduction current beta. What is the magnitude of the conduction current? IC. Magnitude of the conduction current is equal to C dV by dt beta. Okay. So what is this C? C is equal to epsilon naught A by D because it is an air filled. So epsilon naught into A. What is the plate area? 10 to the power of minus 4 divided by 10 to the power of minus 3, which is C is equal to epsilon naught into 10 to the power of minus 1. Okay. And what is the voltage beta here? V is equal to, it is, you can take the cosinusoidal or sinusoidal, which is not mentioned because anyhow we are interested only in the magnitude here. That is the reason why he has not mentioned here. It is 0.5 volts cos or sine. Let us take sine. Sine 2 pi f beta. What is f? 3.6 into 10 to the power of 90. Just substitute all the values here. So conduction current is equal to epsilon naught into 10 to the power of minus 1 into d by dt of 0.5 sine 2 pi into 3.6 into 10 to the power of 90. Differentiate this one. IC is equal to epsilon naught into 10 to the power of minus 1 into 0.5 into, let me turn the page here. The space would not be sufficient. Sorry, what did I say? Let me turn the page here, beta. So conduction current IC is equal to epsilon naught into 10 to the power of minus 1 into 0.5 into 2 pi into 3.6 into 10 to the power of 9 cos 2 pi into 3.6 into 10 to the power of 9 into T. We are interested only in the magnitude beta. Only this one. So what is the magnitude of the conduction current, which is equal to epsilon naught value is 1 by 36 pi into 10 to the power of 9 into pi into 10 to the power of pi into 10 to the power of minus 1 into 36 into 10 to the power of 8 beta. So 36 here, pi here, 36 here, 36 here will go. Sorry. Here in the numerator 10 to the power of 7 divided by 10 to the power of, this will be 10 to the power of minus 2 amperes. Or it will be 10 milliampere is the answer. So magnitude of the conduction current is equal to magnitude of the displacement current, which is 10 milliampere is the answer. So option C, A is the answer beta. Okay. Abhijit. Let me turn the page here. So I will be saying one thing, that there will be a question on identification of equations, beta. How? He will give some set of equations and he'll ask you to identify. These kind of questions are regular questions in the engineering services. In the earlier paper also used to ask these kind of questions, but nowadays to increase the difficulty of the question, there is no such questions. But let us have that question like that. You will find something questions like this. Identify which one of the following equation is not valid for static fields. Option A, del cross H is equal to J. Option B, J is equal to sigma into E. Option C, divergence of D is equal to rho V. Option D, divergence of J is equal to minus dou rho V by dou T. Static fields means what? Dou by dou T must be equal to 0, isn't it? Yes. So anyhow, here dou by dou T, dou D by dou T is missing. That is correct. Well, Ohm's law is valid for static and time varying fields, the same equation. Here is also, it is same for static and time varying fields. So this must be wrong. So this is the answer for the question. Which one of the following equation is not valid for static fields? Okay, these kind of questions are also expected. Okay, beta. Let us have a last topic here. That is the interpretation of the Maxwell's equations. One of your friend is asking, is that 0.5 is a RMS value? Beta, he has given this as a peak value itself. Generally, this format will give the RMS value, right? But if you take that as a RMS value, you need to multiply that one with the root 2. If you multiply that one with the root 2, you need to multiply this one with the root 2. If you multiply with the root 2 1.14, you're going to get. But that is not there in the options, beta. That is not there in the options. See, root 2 value is not there in the options. That is the reason why that must be which value? Peak value. That is how we have guessed. 1.41 must be there, but there is no 1.41 in the options. Yes, that is the reason. No, why you have to divide by the root 2? You have to take that as a peak voltage itself. Here it is a peak voltage itself. Suppose if this is a RMS voltage, then you need to multiply that one with the root 2, isn't it? To make it peak voltage. This is a relation. Hope you know this one. VRMS is equal to VM by root 2. That means if you want to get a root 2, VRMS into root 2. That means you need to multiply this entire thing with the root 2. Here also root 2. So that means you need to multiply this one with the root 2. Answer must be 1.41, but that is not the answer. There is no such option here. So whatever the given value, that must be yes. Fine. Let us go to the new concept. Beta, I'm going to turn the page. Boundary conditions. Listen the theory carefully. Boundary conditions beta. See here, up till now we have considered the medium to be homogeneous. We haven't discussed that much about the medium. We have considered the medium to be homogeneous. Means what? Wherever you see the medium was looking same. Medium is same. But that is not the case in general. The field may interact from one medium to other medium. For example, you do not have that much applications of these boundary conditions, but electronics and communication students will have. We'll take our own scenario also. Electrical engineering, you will have the field interaction from the conductor to the free space. That is one of the most common example, common scenario we'll get our in. For example, plates of a capacitor. The capacitor plate is a conductor. In between them, there is a dielectric. Field interaction from the conductor to the dielectric. Again, dielectric to the conductor. That is one of the simplest example you have. Okay. So what I want to do here, I want to divide the medium into two parts, two mediums. I want to generalize that one. It can be anything. It could be a air, it could be a glass, other one. It could be a air, it could be a wall, it could be a capacitor plate, other one could be a dielectric, whatever it may be. So I'm going to divide this one into two parts beta. Here is the thing. Where this media interface is at L is equal to 0. This is a media interface beta. If I draw a line, if I put a dots here, what does that indicates? It indicates the media interface. Or you can also say boundary interface. So below this one, there is a medium 1. Above this one, there is a medium 2. It could be any medium. Here it could be a copper, it could be a air, or it could be a glass, it could be the air. It could be anything. Okay. What is this one here? It is L is equal to 0 minus. It is L is equal to 0 plus. That means it is just below the interface. Here it is just above the interface. Where is my media interface is? My media interface is here beta. At L is equal to 0. At L is equal to 0, this is a media interface. Below this one, there is a medium 1. Up to here, it is medium 1. Suddenly, it is medium 2. So L is equal to 0 minus is just below the media interface. L is equal to 0 plus is just above the media interface. Okay. So now I'll consider this as a medium 1 beta. Medium 1 will have the medium parameters. Sigma 1, mu 1, epsilon 1. And in the medium 1, there are fields are there here. The electric field, I'll call it as electric field is E1 comma D1. And the magnetic field is H1 comma B1. The field in the medium R, when I say the electric field, it means B1, E1 and D1. And the field in the medium 2 R, here it is a medium 2 beta. Medium 2. Medium parameters are sigma 2, mu 2, epsilon 2. What is the electric field? Electric field is E2 D2 beta. And magnetic field is H2 comma B2 beta. Clear? So that is the medium parameters of medium 1 and medium 2. So ultimately what we want to do in the boundary conditions, writing all the things. So here in the boundary conditions, I want to establish there are fields are present just below the interface here. And fields are present just above the interface. L is equal to 0 minus and L is equal to 0 plus. I want to establish the relation between the fields just below the media interface with the just above the media interface. Here it is L is equal to 0. The fields are present just below the media interface. The fields are present just above the media interface. So the fields above just above the media interface and just below the interface, I want to establish the relation between them. So what we want to do here, we are trying to establish the relation between electric and magnetic fields just below the media interface with the just above the media interface. So the fields here are related to the fields here across the media interface or just below the media interface with the just above the media interface, you can call. Clear? Yes. Just a minute. Just below the media interface with the just above the media interface. Yes. EMS syllabus for the instrumentation and electrical engineering is same beta. Okay, please focus here. So the fields just below the interface and just above the interface, we want to establish the relation here. And what this is called beta? This is called a media interface or boundary interface. This is called media interface or boundary interface. Media interface. Media interface or boundary interface. Then what should I do here? I need to go back to what is called a Maxwell's equations. I need to go back to what is called Maxwell's equations. Maxwell's equations, there are two forms. To deal with these boundary condition problems, I need to go back to the Maxwell's equation. There are two forms of Maxwell's equations. One is the integral form, other one is a differential form. Okay, fine. So the differential forms of Maxwell's equations are not suitable for boundary condition problems. Why? Why? Because it is differentials. Because there is a discontinuity in the medium. Up to here it is medium 1, suddenly it is medium 2. So the integral forms are suitable. Okay. Before that, before writing the Maxwell's equation, there is a one more thing beta. Sometimes what happens, because of the material properties, what happens? Because of the material properties, when I join two materials, up to here it is a glass, suddenly it is the air. Because of these material properties, what happens at the media interface, at the boundary interface, there is a possibility for the charge distribution. There is a possibility for the charge distribution. Charge distribution may happen over the media interface because of the medium properties. Okay, at the surface. So the charge distribution may happen here. It is given by the rho s beta. Units are coulomb per meter square. This is called surface charge. Surface charge may exist. Clear? Sometimes what happens because of these charges, because when I join the two magnetic materials, there is a possibility for the current flow between them. Or you may, according to the application, you may insert the sheet between the two medias. So there may be a possibility for the current flow beta. Yes, this is represented with the current is flowing in the sheet. This is represented with the JS. Units are ampere per meter. This is called surface current. What it is? Okay, fine. So these surface charges and surface current may exist, may not exist. That purely depends on the condition what we are dealing. As I said earlier, the integral forms of Maxwell's equations are suitable here, beta. Which forms are suitable? Integral forms are suitable. Fine. Let me write down those Maxwell's equations. Let me turn the page here. So what are the Maxwell's equations here? There are integral forms of Maxwell's equations. What are they? Closed line integral of HDL is equal to IENC. Current enclosed beta. So what kind of current it can have? It can have a conduction current. It can have a displacement current. For a boundary condition problem, there is a new current. What is that current? Surface current. Number 2 beta. Closed line integral of EDL is equal to surface integral of dou B by dou T into dA. Number 3. It can have closed surface integral of dDA is equal to charge ENC, enclosed beta. Number 4. Closed surface integral of BDA is equal to 0 beta. Dimensionally, these two equations are same beta. Why? Because it is a closed line, And dimensionally, these two equations are same, closed surface, closed surface. So to understand these two equations over the boundary interface, I'm going to consider what is called a closed line. First two equations. I'll consider closed loop beta to deal with the first two equations. This is for the first equation. This is for the second equation. To deal with the second two equations, this is a closed surface, closed surface. To deal with these two equations, I'll consider closed surface across the boundary interface. That means I'll going to consider closed surface here. You must know this derivation. Then only you can make a use of these boundary conditions, because there are some things need to be highlighted. Otherwise, I would have given directly a conclusions. Okay. You should have some idea regarding these boundary conditions, derivations. So this is to deal with the third Maxwell equation and fourth Maxwell equation. So what I'll do here, I'll apply these first two Maxwell's equations over this loop, and I'll make these sides goes to 0 because our information is, our requirement is just above and just below. I'll make these sides goes to 0. So I'll get the information just above and just below. Similarly, remaining two equations beta, I'll apply over this one, the cylinder, and I'll make these sides goes 0. I'll get the information just above and just below. Okay. So this is what we're going to do in the boundary conditions. Let me write down. What are the things we're going to do here? Yes. What are the boundary conditions beta? Let me write down here. The boundary conditions. Boundary conditions establish relation between electric, magnetic fields just below the interface, means L is equal to 0 minus with the electric, magnetic fields just above the interface. That means in brackets L is equal to 0 plus. This is the first point beta. So this is what we're going to do in the boundary conditions. What is the next point? So how this media interface is characterized? Media interface is characterized by its surface charges and surface currents beta. Okay. So that may exist or may not exist. So what it is? The media interface is characterized by its surface charges in brackets rho s coulomb per meter square and surface currents. What are they? Js ampere per meter. Next, third point. Integral forms of Maxwell's equations are suitable for the boundary condition problems. What they are beta? Integral forms of Maxwell's equations are suitable for integral forms of Maxwell's equations are suitable for boundary condition problems. Why like that? Because as medium is discontinuous. Next, Next beta, one more point. The fields in the two mediums are resolved into tangential and normal components to define the boundary conditions. Let me write down. Later, I'll justify that point. Fields in the two regions are resolved into tangential and normal components to define boundary conditions. What does that mean? I'll explain. Okay, see here. Just above and just below is the boundary conditions. Media interface is characterized by its surface charges and surface currents. Okay, and then integral forms are used. And then the fields are resolved into tangential and normal components to the media interface to define the boundary conditions. Okay, beta. Let me draw the figure one more time. This figure. This figure. Okay, I'm going to turn the page here. And we'll do some derivation here. We must do derivations. Without derivation, it would be incomplete discussion on the boundary conditions. Because derivations are required to solve some numericals. During the derivation, we'll get some concepts. Okay, so those concepts are required to solve the numericals. That is the reason why we'll take this derivation. Fine. Observe here, beta. Here is a media interface. Yes, here it is L is equal to 0. Here it is L is equal to 0 plus. Here it is L is equal to 0 minus beta. Here it is a media interface or boundary interface, you can call. Here it is medium 1 beta. And parameters are sigma 1, mu 1, epsilon 1. And what is the electric field here? E1 comma D1. What is the magnetic field here? H1 comma B1. Here it is medium 2 beta. Sigma 2, mu 2, epsilon 2. Here it is E2 comma D2. H2 comma B2 beta. What I'll do, I'll resolve the fields are present in the medium 1 and medium 2. These fields, electric and magnetic fields. For our mathematical convenience, I'll going to resolve into tangential and normal components. Normal to the interface, tangential to the interface. I'll represent all the four fields in the tangential form and normal form. That is what I've written here. What did I write? Fields in the two regions are resolved into tangential and normal components to define boundary conditions. That is the story. Clear, beta? Yes. Okay, so let me write down those things here. I'm going to resolve all the fours, 1, 2, 3, 4, in the medium 1 as well as in the medium 2 into tangential and normal components. Here it is like this. Here it is HT1. Here it is HN1. Here it is ET1. Here it is EN1. Here it is DT1, DN1, BT1, BN1. Here it is HT2, HN2. Here it is ET2, EN2, DT2, DN2, BT2, BN2. As I said earlier, to deal with first two equations, I'll going to consider the loop across the media interface. And there is a current flow here, beta. How much is the current flow? Current is flowing on the sheet here, which is in between, which is placed between the two mediums on the interface. So here it is JS. Units are ampere per meter. Here is a loop. Here it is a loop direction. I'll consider like this in the anti-clockwise direction. Then why you can argue, why can't we cannot take it as a clockwise direction? Clockwise is also true. You can take in that way also. So here it is A, here it is B, here it is C, here it is D. And I'll consider the sides as delta W. Side has a delta W. Clear? So to deal with these two equations, I'll consider what is called a cylinder, as I said earlier. To deal with those two equations, I'll consider a cylinder across the media interface. And remember, there is a charges here. Rho s coulomb per meter square. And I'll consider normal direction in this way, beta, for this one. I'll consider normal direction in this way. Here it is n cap. Obviously, this will become minus n cap. You can ask why I have not taken in the reverse manner. Reverse manner also you can take. And this is a side. I'm taking it as a delta W. And the cross section of this one is, I'll take it as a delta A. Okay. Now let us start the analysis, beta. Let us consider one equation after other equation, other Maxwell's equations. From there, you can get the things. I'll go to turn the page here. Consider the first Maxwell equation. What is the first Maxwell equation? Closed line integral of HDL is equal to I ENC beta. Okay, I'll going to apply this one over this loop, ABCD loop. And inside that, there is a current. What kind of current is that? That is a surface current. So what happens to this one? This will become integral is from A to B HDL plus B to C HDL plus C to D HDL plus D to A HDL is equal to line integral of Js into dl beta. Now let us consider what is called, our interest is, we want to find it for what? At the media interface, just above and just below the media interface. That means at boundary interface or media interface. Our interest is just above and just below. So what should I do? I should make this delta W strings to 0. That means integral B to C and integral D to A will go 0. Yes. So what happens at the media interface or boundary interface? At the boundary interface beta. What happens at boundary interface? Side strings to 0, delta W strings to 0 beta. So what are the integrals will go 0? Integrals B to C will be 0 and D to A will be 0. Integral B to C is 0. And integral D to A will be 0. Then what happens from integral A to B? Integral A to B. Integral A to will have only this dot product. Why? Because this is normal. That dot product will be 0. Because the line is like this, HN1 is like this. So they are 90 degrees to each other. So only there will be a tangential component dot product. That means this will become A to B HT1 into DL. Similarly, C to D is like this beta. HT1 is like HT2 is like this. This is normal. Normal component is perpendicular. It is making 90 degrees. So dot product contribution will be 0. So the dot product will be there only due to the tangential component. But that too, especially here, the loop direction is like this. HT2 is like this. They are opposite direction. So what happens? You're going to get here minus. Minus C2D HT2 into DL, which is equal to Js into DL beta. Just to remove the integrals on both sides. So what you're going to get? HT1 minus HT2 is equal to Js. So this is the first boundary condition beta. I'll call this as the first boundary condition. So the difference in beta, see here, as I've considered the loop in the anti-clockwise direction, you have got HT1 minus HT2. Suppose if I would have considered in the clockwise direction, then the difference would be HT2 minus HT1. Okay, yes. So how you need to remember is something like this. Difference in the tangential components of magnetic field intensity is equal to surface current. Clear? So the difference in the tangential components of magnetic field intensity is equal to surface current. So what I have done here, I have applied this Ampere's law, the first Maxwell equation over this loop, and I have made side strings to 0. I have made sides 0. So if I compress this loop, I'll get the information just above and just below. That is what the boundary condition is all about. Let me turn the page. This is one of the boundary condition beta. Let me derive one more boundary condition. For that, let us consider the second Maxwell equation. Consider second Maxwell equation. What is the second Maxwell equation beta? Here it is. Closed line integral of EDL is equal to surface integral of dou B by dou T into dA beta. Expand this one, apply this one over that. So here it is A to B E dot dl plus B to C E dot dl plus C to D E dot dl plus D to A E dot dl, which is equal to minus surface integral of dou B by dou T into dA beta. Where is our interest? Our interest is just above and just below the interface. At the boundary interface, what happens, beta? Boundary interface, or you can also say media interface. At boundary interface, delta W strings to 0 beta. That means what are the integrals will go 0? Here is a loop beta. You are making side strings to 0. There will be, if I compress the loop, you will going to get one line above and one line below. The area will also be disappear. If I compress the loop, what happens? The area will disappear. Yes or not? If I compress the loop, the area will disappear. Simple logic. So here is a loop like this. Here is a loop like this. If I compress this one, is there any area inside that? No area. There will be one line above, one line below. So what I mean to say here is, what are the integrals will go 0? B to C will go 0, D to A will go 0, B to C, second integral and third integral will go 0. Second integral and fourth integral. B to C, D to A will go 0. And also this area will go 0. Isn't it? Here is a loop. Here is a loop. If I compress this loop, this will become a line. Is there any area inside that one? No. There is a loop. So that area will also go 0. Clear, beta? Yes. So there will be an integral from A to B and C to D. So the A to B is like this and T1 is like this. So this dot product will survive. This dot product will go 0. And here, beta, here the loop direction is like this, electric field is like this. So they are opposite direction. So you will going to get minus sign there. So here what you will going to get is A to B ET1 into DL minus C to D ET2 into DL is equal to 0. Suppress the integration. So you're going to get ET1 minus ET2 is equal to 0. ET2 is unconditionally equal to ET1. Is the second boundary condition, beta. Second boundary condition, what it is? Tangential component of electric field intensity is always continuous across the dielectric media interface. Is always same in the two mediums across the media interface. Okay, let us take the third boundary condition, third Maxwell equation. I'm going to turn the page here. Consider the third Maxwell equation. Consider third Maxwell equation, beta. What is the third Maxwell equation? Closed line integral of dA is equal to charge ENC, beta. Expand, apply this one over that closed surface, what we have considered. Apply this one over this. So this cylinder will have top, bottom, and sides. And inside that one, there is a charge. How much is the charge, beta? It is a surface charge. So I can expand this one as top surface D dot dA plus bottom surface D dot dA and sides into D dot dA, which is equal to what is the charge inside that surface? It is a surface charge. Rho s into dA beta. Okay. So where is our interest? Our interest is at media interface or boundary interface. At boundary interface. At boundary interface, delta W strings to 0 beta. So what are the integrals will go 0? Let me go back. That means you need to compress this cylinder. If I compress the cylinder, what I'm going to get? Here is a cylinder. If I compress this one, I'm going to get the area. The volume will disappear, sides will disappear, but you're going to get a disc. One disc above and one disc below. Area will be there, but volume will disappear. Sides will disappear. What I mean to say here is, so the sides will disappear here. This means sides integral will go 0. That's all it is. And what about for the top integral beta? For the top. For the top, only the dot product will be contributed by only dn2. dt2 is the tangential component. The dot product will go 0. And here it is dn1. The normal is downwards for the down one, for the bottom one. So what I mean to say here is, here it is top. Top is dn2 into dA minus bottom. Bottom is dn1 into dA, which is equal to rho s into dA. Suppress the integrals on both sides beta. So you're going to get dn2 minus dn1 is equal to rho s beta. So this is a third boundary condition. One, two, three. So how you need to remember beta? See here, I have considered positive normal above. So that is the reason why dn2 minus dn1. Suppose if I would have considered the positive normal below, then this would be dn1 minus dn2. So how you need to remember is the difference in the normal components. Difference in the normal component of electric flux density is equal to surface charge. See here, let me show you with the examples here. Example number 1 beta. Here it is of medium 1. Here it is a medium 2. Suppose if the normal is acting like this. Something, let us start like this. Here it is medium 1. Here it is medium 2. Suppose if the positive normal is acting like this. So you need to take the difference towards the positive normal. So then how you have to take the boundary condition here? dn2 minus dn1 is equal to rho s beta. Suppose if it is a reverse beta, what I mean to say is this one. This is a media interface. This is medium 1. This is a medium 2 beta. My positive normal is acting like this beta. So then how you have to take the difference? dn1 minus dn2 is equal to rho s beta. That is all the story is. Clear? Yes. So this is a third boundary condition. Now let us have a fourth, last boundary condition. I'm going to turn the page. Consider Fourth boundary condition. What is the fourth boundary Maxwell equation? Closed surface integral of B dot dA is equal to 0. Expand this one. There is a top one, B dot dA, plus there is a bottom one, B dot dA, plus there is a sides integral, B dot dA is equal to 0. But where is our interest? Our interest is at the boundary interface or media interface. At boundary interface, delta W strings to 0 beta. Means sides will go 0. And you can check out what is this top will become. Bn2 into dA minus what is this bottom will become. Bn1 into dA is equal to 0. So here it is. Bn2 minus Bn1 is equal to 0 beta. So here it is. Bn2 is unconditionally equal to Bn1. Here it is number 4 beta. That is the story. So the normal component of magnetic flux density is always continuous across the dielectric media interface. So what are the boundary conditions we have got so far? Let me summarize them. I'm going to turn the page. This is what we need to remember for our exam. Dielectric to dielectric beta. Dielectric to dielectric. Excuse. The other one is dielectric to conductor beta. Dielectric to conductor is a special case of dielectric to dielectric beta. Okay, first let me write down what are the boundary conditions we have. First one is HT1 minus HT2 is equal to JS. Second one is ET2 is unconditionally equal to ET1. The third one is DN2 minus DN1 is equal to rho S. The fourth one is BN2 is unconditionally equal to BN1. Okay, beta. Then you want to obtain it for the dielectric to conductor beta. What is the meaning of dielectric to conductor? Inside the conductor, we have already seen that there is no electric field, there is no magnetic field. All the fields are 0. Mar gaya. Mar jayega. No EM phenomena can survive inside the perfect conductor. Isn't it? So let us consider conductor is 1, medium 1. Dielectric is medium 2. So if you want to get it for the dielectric to conductor interface, I should make this one equal to 0, this one equal to 0, this one equal to 0, this one equal to 0. I should make all the fields 0 in the conductor. So here it is, minus HT2 is equal to JS beta. Number 2 is ET2 is equal to 0. Number 3 is DN2 is equal to rho S beta. Number 4 is BN2 is equal to 0. There is no need for giving the numbering here. The numbering will be given when the fields are existing in the two mediums. We know that these are the fields which are existing on the conductor. Inside the conductor, no field can survive. So there is no need for writing this subscript 2, 2, 2, 2. It is already clearly evident that the fields can survive only on the conductor. So what I will do, I'll going to modify this as H tangential is equal to J. Yes. Along with the negative sign, I have written a HT. Here, E tangential is equal to 0. Here, D normal is equal to rho S. Here, B normal is equal to 0. So, for the dielectric to conductor, these are the boundary conditions. This is something we already know. How the electric field can exist on the conductor normally, not tangentially. Tangential electric field on the conductor is 0. Normal magnetic field cannot exist. Magnetic field exists tangentially on the conductor. We need to do some interpretation of those things. So ultimately, what you need to remember here is this box, what I have mentioned here. You no need to remember this one. You can obtain whenever it is required from here. Just you need to remember these 4 boundary conditions. What it is? HT1 minus HT2 is equal to JS. Next one, ET2 is equal to ET1. Next one, DN2 minus DN1 is equal to rho S. Fourth one is BN2 is equal to BN1. We'll do some small interpretation of these things with the help of some diagrams so that you can connect yourself properly. Okay. So what we'll do that small interpretation followed by the numericals. We'll take numericals. Okay. So now what we'll do, we'll go for a 15 minutes break. After that, we'll continue with the remaining things. Okay, welcome back. How to decide JS direction? I'll explain. I'll explain everything while discussing the numericals. Okay, beta, see here. Let us try to focus a little bit more on this one. Let us try to have some interpretation of these equations. I'm going to turn the page here. For example, beta, this is a media interface. Here it is a interface, beta. Here it is a air, beta. This is a perfect conductor. Perfect conductor means conductivity tends to infinity, beta. Okay. So here inside the perfect conductor, the electric field is 0. So that will make the H2 0 and D 0 and then B 0. So all fields are 0 inside the perfect conductor, isn't it? All fields are 0 inside perfect conductor. Now let us say there is a charge here. What is the charge, beta? Rho s. Units are coulomb per meter square. So how does the electric field exist? Let me go back here. What these boundary conditions are, it is saying that electric field E normal is equal to rho s by epsilon, and then E tangential is equal to 0, and then H tangential is equal to Js, and then H normal is equal to 0. So that is how the boundary conditions. What it is saying, the electric field can exist only normally on the conductor. Yes, we know from the knowledge of electrostatics and magnetostatics, we know that electric field can survive only normal to the conductor. If there is a charge like this, so electric field cannot exist like this. How it can exist is a normally like this. So how it can exist normally? E normal, E normal, E normal, and E normal. Okay. And one more thing here, if the current flow happens like this, that is all about this interpretation. So how the electric field can exist on the conductor? Normally, better. Suppose if the current flow is happening like this. What is this current flow is Js beta. Js units are ampere per meter beta. So if the current is flowing like this, the magnetic field is like this. If the current is flowing like this, magnetic field is like this. If the current is flowing like this, magnetic field is like this. That means the magnetic field is like this. That means if the current is flowing like this, magnetic field is like this. This is the current flow direction. This is the magnetic field. So how the magnetic field is tangential? So here it is H tangential, H tangential, H tangential, H tangential. So the magnetic field cannot exist normally on the conductor. It can exist only tangentially. Electric field cannot exist tangentially. It can exist only normally. Excuse. Right? That is the interpretation of these equations. Now let us take the questions here, beta. Let us have a questions here. I'm going to turn the page. The displacement flux density at a point on the surface of a perfect conductor is D is equal to 2x cap minus √3 into z cap coulomb per meter square and is pointing away from the surface. The surface charge density at the point will be at the point coulomb per meter square will be. Options are given to option B 4 minus 2, option C 4, option D minus 4. The displacement flux density at a point on the surface of the perfect conductor is D. D is this one. Is pointing away from the surface. The charge density, surface charge density at that point will be. Beta, where this is observed? The displacement flux density at a point on the perfect conductor. This is observed on the conductor, beta. Is asking the surface charge. So what kind of boundary conditions you have to choose? There are two types of boundary conditions. One is dielectric to dielectric, other one is dielectric to conductor. So this electric flux density is observed on the conductor beta. So you have to use dielectric to conductor interface boundary conditions. That means you have to use this one. And asking the surface charge rho s. So what is the surface charge is rho s is equal to dn. So this is nothing but dn magnitude beta actually. Whatever he has given, this must be a normal component. Why? Because tangential component cannot survive. What is ET? ET is always 0. Epsilon into ET is always 0. dt is equal to 0. So whatever he has given, it must be a normal component. Okay. So what is the surface charge beta here? Surface charge rho s is equal to, you have to take the magnitude of this one. What is the magnitude of that? Square root of 2 square plus minus 2 root 3 square. So the rho s is equal to square root of 4 plus 4 into 3, which is square root of 4 into 4, which is plus or minus 4 coulomb per meter square. So here it is plus 4 coulomb per meter square, other one minus 4 coulomb per meter square. There are two possibilities are there here, beta. Then what is the answer? Is it a plus 4 coulomb per meter square or minus 4? Yes, beta. Is it a plus 4 coulomb per meter square or minus 4? It is a plus 4. It is clearly mentioned. It is pointing away. Thus happens only if it is a positively charged one. It is away. So this is the answer. So option C is the answer, beta. Let me turn the page here. Okay. Now let us take one more question here. Let us take one more question, beta. The electric field across a dielectric air interface is shown in the given figure. The surface charge density on the on the interface is, options are given -4 epsilon naught, option B, -3 epsilon naught, option C, -2 epsilon naught, option D, minus epsilon naught. This is the diagram he has provided. Here it is epsilon is equal to 2 epsilon naught. Here epsilon is equal to epsilon naught. Here it is E is equal to 2x cap. Here it is E is equal to x cap. Yes, beta, what is the answer for that? Yes, beta. So he has not mentioned what is a positive normal here. He has not mentioned what is a positive normal here. Okay, doesn't matter. So I'll take something like this. I'll call this as a medium 1. This is a medium 2. This one is E1, this one is E2 beta. Because he has not mentioned anything here. So how do you find out the surface charge? He's asking for the surface charge. What is the surface charge? dn2 minus dn1 is equal to rho s. Then you can ask why I have considered dn2 minus dn1. Nothing is specified in the question. I can take dn1 minus dn2 also. So to avoid the confusion, in the options he has given all the values to be negative, isn't it? So expand this one. Here it is epsilon 2 into en2 minus epsilon 1 into en1, which is equal to rho s beta. Yes. So here it is epsilon 2 is how much? Epsilon naught. And what is the normal component? Here it is 1 into 1 minus epsilon 1 is 2 epsilon naught into normal component is 2. So here it is epsilon minus 4 epsilon naught is equal to rho s beta. So the rho s is equal to minus 3 epsilon naught coulomb per meter square. Beta, if I would have considered in a reverse manner, I would have got plus here. But in the options, there is no plus 3. Because in the question he has not specified what is a normal. That is the reason why he has maintained that clarity in the options. There is no option like a +3 epsilon naught. Yes. So here this is the answer. Clear? Yes. Fine. Let us take one more question. I'm going to turn the page. A plane z is equal to 0 separates two media where medium 1 is defined for z less than 0 and with the medium parameters and with the medium parameter epsilon 1 is equal to 2 epsilon naught and medium 2 is defined for z greater than 0 with medium parameter epsilon 2 is equal to 4 epsilon naught. Okay. If electric field in medium 1, if electric field in medium 1 at interface is E1 is equal to 2x cap plus 4y cap plus 6z cap volt per meter. Find electric field in medium 2 at interface. Assume media interface to be charge free. Assume the media interface to be charge free beta. Yes, what should I do? I should draw some diagram here. See here. Today, if I take up to 10:30, I can finish this subject. But the most of the students are not ready. And management was also not ready. So that is the reason why we'll finish this today's session a little bit early so that we can spend around some 1.5 hour session in the tomorrow. Let us finish all the electric field boundary conditions in a today's session. In the tomorrow sessions, we'll take the magnetic field boundary conditions. Okay. A plane Z is equal to 0 separates the two media where medium 1 and medium 1 is defined for Z less than 0. Let me turn the page here. Let us draw some rough diagram here. I'm going to turn the page here. So Z is equal to 0 is a media interface beta. What it is? Z is equal to 0 is a media interface. Let me draw Z is equal to 0 plane. Here it is x-axis, here it is y-axis, here it is z-axis. This is a media interface beta. This is xy plane is a z is equal to 0 plane. Here it is z is equal to 0 is a xy plane beta. Yes, you can also call it as a xy plane. And one more thing beta, here there is no surface charge. That means rho s is equal to 0. That is what mentioned in the question. Yes, so here it is a xy plane. And this one is z less than 0 beta. Here it is z greater than 0. For z less than 0, it is medium 1 beta. And with the medium parameter, epsilon 1 is equal to 2 epsilon naught. That is what mentioned in the question itself. So for z less than 0, it is medium 1. Medium 1 is defined for z less than 0. With the medium parameter, epsilon 1 is equal to 2 epsilon naught. And medium 2 is defined for z greater than 0 with the medium parameter, epsilon 2 is equal to 4 epsilon naught. Electric field in the medium 1 at the interface is given beta. That means E1. How much is the E1? E1 is equal to 2x cap plus 4y cap plus 6z cap volt per meter. Here it is medium 2 beta. What are the medium parameters? Epsilon 2 is equal to 4 epsilon naught. Is asking what is the electric field E2 beta. Beta, here z is equal to 0 plane. It is a xy plane, isn't it? How the x and y are? X and y are tangentials and z is a normal. Here z value is minus infinite. Here z is equal to 0. Here z is equal to plus infinite. So z value is like this. X and y are tangentials. Z is a normal. X and y are tangentials and z is a normal to the interface. In a simple way, you can remember whichever is constant, that itself is a normal and the remaining are the tangential components. So you need to identify the tangential and normal components first here. Because the boundary conditions are defined for tangential and normal components. Here it is ET1. Here it is EN1. Okay, beta. Fine. And what is the normal here, beta? The positive normal is in the Z direction from medium 1 to medium 2. Yes. So you need to take the difference. How? This is a positive normal is from 1 to 2. So you have to take medium 2 minus medium 1 when you are taking the difference of the boundary conditions, especially for the dn2 minus dn1. Now you can proceed. Let me turn the page here. What are the boundary conditions we have? ET2 is equal to ET1 beta. You can write this one in the vector form, which is equal to how much? What is this ET2? It is 2x cap plus 4y cap. So that is how you have got a tangential components. What about the normal component beta? There is no direct boundary condition for normal component, but there is this boundary condition. dn2 minus dn1 is equal to rho s. Here the surface charge is equal to 0 beta. So here it is dn2 is equal to dn1 beta. So here it is epsilon 2 into en2 is equal to epsilon 1 into en1. So en2 vector is equal to epsilon 1 by epsilon 2 into en1 vector. You can write this one in the vector form as well. Clear beta? So what is this en2 beta? Epsilon 1 by epsilon 2. What is epsilon 1? 2 epsilon naught divided by epsilon 2. What is epsilon 2? 4 epsilon naught. Into normal component. What is the normal component? 6 z cap. Here it is 6 z cap. En2 is equal to 3 z cap. What is E2 is equal to? ET2 plus En2 beta. So what is this ET2? 2x cap plus 4y cap plus 3z cap. Units are volt per meter. Okay, very good. Yes, it is from dielectric to dielectric because this is having medium parameter. Epsilon 1 is equal to 2 epsilon naught. It is the other dielectric. Okay, that is how you need to approach beta. So you, for a given case, you need to identify the this boundary and which boundary conditions. You have to identify the tangential and normal components separately, and you need to proceed. Clear? Let me turn the page here. Now, I'll just change the question. Repeat the previous question for non-zero surface charge, non-zero surface charge density of rho s is equal to 4 epsilon naught coulomb per meter square. Yes, beta. So the surface charge density is present here. Yes, how can you do this one? Is there any change in the tangential component in the previous problem? There is no change in the tangential component. Tangential component remains the same. That means ET2. ET2 is unconditionally equal to ET1, which is equal to how much? 2x cap plus 4y cap. But there will be a change in the normal component beta. Why there is a change in the normal component? Yes. Why? Because you have to take the difference from the positive normal side. So this minus this, dn2 minus dn1, because there is a surface charge here. So here you will find different thing. dn2 minus dn1 is equal to rho s beta. So here epsilon 2 into en2 minus epsilon 1 into en1 is equal to rho s. en2 is equal to rho s plus epsilon 1 into en1 divided by epsilon 2. Just to substitute those values here. Rho s how much? 4 epsilon naught plus epsilon 1. How much is epsilon 1 beta? 2 epsilon naught. Into en1. What is en1? 6. 6 divided by epsilon 2. What is epsilon 2? Is 4 epsilon naught, which is equal to 4 beta. So which component is that? If you want to write in the vector form, it is the z component. So what is the overall? E2 is equal to ET2 plus En2, which is equal to 2x cap plus 4y cap plus 4z cap is the answer. Let us have one more question. I'm going to turn the page. Two dielectric media with permittivity square root of 3 comma 3 are separated by a charge free boundary as shown in the figure. The electric field intensity in medium 1 at point P1 has magnitude E1. The direction of the direction of the electric field intensity at point P2 alpha 2 is where alpha 1 is equal to 60 degrees. This is a diagram provided in the question. Options are also given. Sine inverse of square root of 3 E1 by 2. Option B 45 degrees. Option C cos inverse of square root of 3 E1 by 2. Option D 30 degrees. Here is a diagram. Here it is E1. Here it is alpha 1. Here it is E2. Here it is point P1. Here it is point P2. Here angle is alpha 2. Here epsilon 1 is equal to 3 epsilon naught. Epsilon 2 is equal to 3 epsilon naught. And he has also said that there is no surface charge here. Charge free. So he is asking for the value of alpha 2 beta. The medium parameters, everything is given. We have developed the boundary conditions for tangential and normal components. But here the electric field is oriented in the arbitrary direction. Can you find out? Yes, we can. We need to resolve into the tangential and normal components beta. So I'll resolve this one into the tangential and normal components. Here it is tangential to the interface. I'll call it as the ET1. Here normal to the interface. I'll call it as the EN1. This is alpha 1. This is also alpha 1. I resolve into the components here. Like this and like this. Here it is EN2. This one is ET2. Clear beta? I'll going to turn the page here. What is this EN1? EN1 is equal to E1 into cos alpha 1. ET1 is equal to E1 into sin alpha 1. Similarly, what is EN2? EN2 is equal to E2 into cos alpha 2. What is this ET2 beta? ET2 is equal to E2 into sin alpha 2. So I have resolved into the tangential and normal components. So use the appropriate boundary conditions. What are the boundary conditions we have? ET2 is equal to ET1. What is ET2? E2 sin alpha 2 is equal to E1 sin alpha 1. Let me call this as equation number 1. What is the other boundary condition? dn2 minus dn1 is equal to rho s. You can take a difference whatever the way you like. Why? Because here it is a such charge-free region. So here it is dn2 is equal to dn1. Epsilon 2 into en2 is equal to epsilon 1 into en1. So here it is epsilon 2 into en2. What is en2? E2 cos alpha 2 is equal to epsilon 1 into what is en1? E1 cos alpha 1. Let me call this as equation number 2 beta. So I'll divide 1 by 2 beta. 1 divided by 2, which is E2 sin alpha 2 divided by epsilon 2 into E2 into cos alpha 2 beta, which is equal to E1 sin alpha 1 divided by epsilon 1 into E1 into cos alpha 1, which is tan alpha 2 by epsilon 2 is equal to tan alpha 1 by epsilon 1. Here it is tan alpha 2 is equal to epsilon 2 by epsilon 1 into tan alpha 1. Just substitute all the values. Epsilon 2 by epsilon 1. What is epsilon 2? Square root of 3 by epsilon naught. 3 into epsilon naught into tan of how much is 60 degrees. So here it is 1 by root 3 into root 3, which is equal to 1. So alpha 2 is equal to 45 degrees is the answer. I am adjusting here itself. So option B is the answer. So these are the varieties of boundary conditions on electric field. We need to discuss the magnetic field boundary conditions with current, without current. With current is little bit, you need to take care about the cross product and all that story. I need to discuss some small note and small theory followed by the problems. Okay, but that I'll postpone to the next session. It hardly requires 1.5 hours of lecture. Okay. So now what I'll do, let us open our discussion for the doubts. Clear, beta? Because I cannot extend up to 10 or 10:30 PM today. That is the reason why we'll nicely plan tomorrow. Let me open the discussion for your doubts. Yes, Vishnu Ajit.
Sir,
Ah,
capacitor, sir, that how that displacement current and the incoming current are same. That I lost my net connection in between. Yes, sir.
Between the two plates,
Oh.
a time varying electric field is established.
Yes, sir.
Time varying electric field will give magnetic field.
Yes, sir.
Okay. So here the magnetic field is supported by the flow of electrons.
Yes,
In
sir.
between, the magnetic field is supported by the
Displacement current.
electric field. So the continuity of the magnetic field is maintained throughout the circuit. So it acts like a closed one.
Yes, sir.
So here there is a current flow. Here there is a current flow. Here there is a current flow. The
Okay.
current flow here and current flow here must be same, isn't it?
Yes.
Obviously, which must be equal to this one.
So same like series concept.
Same like a series concept.
Okay. Sir, and in the case of the boundary condition also, we are just compressing the Amperian loop we are considered, no, sir?
Yes, yes. Compressing in the sense our interest is just above and just below the media interface. It is a boundary condition across the media interface.
So
we are using
that media has a thickness, sir.
Obviously this see this is a mathematics. You are not compressing the medium. You are just applying over the loop and you are making that sides goes to 0 so that I'll get the information just above and just below.
Like more like a limit, like a limits, applying limits, like if
Yes,
it is
yes, exactly.
delta W it is sentence. Sir,
Yes.
and my last doubt is regarding this sheet, sir. The sheet concept is quite disturbing for me, sir. In the sheet, how is this current flowing, sir, actually? Like wires, okay, you can understand, you apply some potential difference or when there's a variation in electric field, it flows. But the sheet concept is quite, it has been disturbing me, sir. Like how will this charges flow on the sheet? Like does it form in a streamline line fashion or will just spread out like a water river sort of?
It is something like yes, water flowing on your floor.
So but again for any charges to flow there must be a potential difference, no, sir? But again if you give any potential difference across edges also, since all the sides are shorted, then how does it flow?
So if you see, if there is a sheet here, and if you connect some potential difference here, is there won't be any current flow? If you have a sheet like this, some conducting sheet, and if I connect this, take some tip here, connect it to the battery, is there won't be any current flow on this one?
It will be, sir, but wouldn't it be localized, like wouldn't it be streamlined, just one conduction channel sort of?
No, there will be distributed. Charges are distributed like this. At least it will flow for a certain region. It may not be spread over the entire sheet. At least the current will flow like this, at least like this. So this part can be seen as a sheet current.
Okay, sir. Thank you, sir.
Yes,
sir.
Mr. Swain.
Sir, I have doubt on that derivation, sir.
Which derivation?
Sir, the path chosen for that line integral, sir. Yes, sir. Here, this is, let us assume that that plane is like XY plane and Z axis is above. Not, sir, that your derivation for that boundary value condition.
First derivation.
First derivation.
Hmm.
That surface we are taken. Yes, sir. Here, sir, this is a surface where in the x direction it is flowing, means that surface charge, and the line is the perpendicular is the in the y direction, means I am assuming that y is inside that plane, means our plane, means if we will call like this, right hand thumb rule, here we can see that the plane should be like a flat, means A, B, C, D will be like on the surface, because the line which is perpendicular to that surface is crossing in the y direction, means assuming that this is x that we are showing, inside that there is Y and
See here,
uh,
see here. See, just for showing for you, I'll consider the current like this.
okay. Actually current is inside. That is
Inside or outside, whatever it may be like this,
okay.
or it may be like this, like this.
Mhm. Otherwise, the cross will be not satisfying. Actually.
Yes, yes.
Okay. Sir, for the preparation, the whole preparation of that subject, this subject,
Oh,
means to remember of the derivation, first we have to write
no
on a paper.
derivation, nothing. Only the numericals and formulas and concepts.
Uh,
I've not done any derivations, right?
Derivation means that how to means in the maximum case we are using divergence and Stokes theorem.
Yes.
Maximum means that only that every case we are using divergence and Stokes theorem.
Yes.
To write on a paper and read it means numerical if means numerical from EC paper also.
EC paper also.
Means some conceptual numerical electrical less questions are till we are getting.
Yes, and electrical this ESC paper also.
Sir, I am using conventional some paper.
Electrical ESC prelims and conventional also.
Yes, sir.
These are the minimum essential things you have.
Means
Hope
because
you would have seen that conventional paper. How you felt that conventional questions electrical?
sir.
You've gone through them.
Yes, sir. I gone through that EC paper. EC
paper, electrical paper. First to do it for the electrical. How
okay.
you felt? How was the questions? When you saw these previous conventional ESC papers, from there also you learn some new concepts, isn't it?
Yes, sir. That concept of that I regularly face that EC paper that KQ by R for potential. That concept it is getting that rho L DL it is taking means some concept that some little problem we have done on potential on that
Yes.
because rho L into DL that concept we are using Q KQ by R nearly, but for potential
You learn some concepts also. You will update your subject.
Yes, sir. Definitely.
So solve GATE, solve engineering services prelims as well as mains.
Yes, sir.
First solve mains and then come to the prelims.
Because sir, it is just means completed. If I will do, then it will be clear. Yes. Otherwise, after some days, it will be difficult to revise it.
Yes, yes.
Okay, sir.
Mr. Sen, okay, good. Bilendu, Mr. Sen. Am I pronouncing your name correctly?
Bimalendu Swain from Odisha, sir.
Orissa, okay. Bimalendu Swain.
Farmer family, sir. From farmer family, sir. From farmer, sir. Swine.
Very good, very good.
Okay. Thank you, sir.
Okay, better. Any more questions? Okay, then I'll going to close the session. We'll continue tomorrow with this boundary condition problems on magnetic fields. Bye, friends. Take care.